Welcome back to this course on nanostructured materials, synthesis, properties, self assembly and applications. Today, we are going to start the first lecture of module 4, and we are going to discuss the subject area of photocatalysis, and we have 3 lectures on photocatalysis in this module, and today will be the first lecture of photocatalysis. So, before we go to photocatalysis, briefly we want to look at what is catalysis and what are catalysts. So, if you look around in all the living beings and life processes around us, lot of enzymes are participating and in all parts of the cycle of life, and these enzymes are nothing but catalysts, and they are being used for the formation, the growth and the decay of these living organisms, and are part of the life cycle of all living creatures and flora and fauna on this planet and elsewhere too. Now, the catalysts and catalysis contribute great part in the processes of converting solar energy to various other forms of energies. So, for example, all our food, which is the plants and all the agricultural products, are basically grown, the hydrocarbons or the carbohydrates are made in the presence of solar radiation by photosynthesis by the plant. So, you convert carbon dioxide and water in the atmosphere to hydrocarbons, which is food, and oxygen is generated. So, this photosynthetic process involves several catalytic cycles and is a very important reaction mechanism which people have understood over large number of years. Now, the catalyst also plays a important role in maintaining our environment. Example, recycling of carbon dioxide in the presence of hydrogen. So, the carbon dioxide emissions are converted to other forms of carbon hydrogen compounds or carbon hydrogen oxygen based compounds by several catalysts, and several are natural processes, and now there is tremendous interest in research and development of technologies which convert carbon dioxide produced in our atmosphere into carbohydrates through catalysts. So, these are some of the most important processes we are talking about. We are talking about the life processes, we are talking about photosynthesis, one of the most important process for maintaining life on the planet, and we are talking of reducing carbon dioxide in the environment and bring down the pollution in the environment. So, in all these important global processes, catalysts play a very important role. Now, if you look at the importance based on the chemical industry, we can see that there is an annual sale of catalysts of around $2 billion. And if you look at chemicals that are all related to catalysts, not exactly catalysts, then the sale goes even 100 times more. So, it is $200 billion is the annual market for chemicals that are related to catalysts. 90% of chemical industry has processes which are catalytic, which have catalysts during somewhere in the process. So, chemical industry uses a lot of catalysts in their technology, and overall 2% of the total investment in a chemical process, in a chemical plant, is towards catalysts. So, what is catalysis? This is a brief introductory few points which everybody at this level who is taking this course probably has read somewhere or the other, but it is good to go over few of the key concepts of catalysis before we go to photocatalysis. So, what is catalysis? It is an action where part of in a where this action takes part in a chemical reaction and can alter the rate of the reaction without being consumed or destroyed at the end of the reaction. So, the catalyst is actually going to take part in the reaction, but is not going to be used up at the end, and during this reaction the reactants are going to be converted into products. There are three key aspects of the action of a catalyst. It takes while it takes part in the reaction, it will change itself during the process by interacting with other reactant product molecules, and then it will be regenerated at the end of the reaction. It alters the rates of the reaction. In most cases the rates of the reactions are increased, but in some cases the rate of some reactions which are not desirable can also be decreased, and here the catalysts are also called as catalytic poisons, returning to its original form. So, it takes part in the reaction, it alters the rate of the reaction, and finally, it has to return to its original form. So, after reaction the catalyst with exactly the same nature is reborn or regenerated, and in actual practice however, after going through few hundred cycles or few thousand cycles which depends on each catalyst, the activity of the catalyst goes down, and so every catalyst has a lifespan, and how good is your catalyst is dependent on how long is this lifespan, for how many cycles the catalyst can function without getting deteriorated. So, that is an important part of a catalyst, and an industrial catalyst has to be economical and hence should be able to be used for a large number of cycles. Now, the reaction kinetics and mechanism. How does a catalyst actually change the rate of a reaction? And if you want to understand the change in the rate of a reaction compared to a process which is not using a catalyst, then you can look at this plot, which is a very important plot in the subject of catalysis, where you are looking at the change in the energy of the reactant and during the reaction process. So, as the reaction is proceeding, if you have no catalyst, then the energy profile is given by this top curve. So, as the reaction is progressing, the energy is increasing, goes over a maximum and then decreases, and finally, you get the product, and so the energy of the product is lower than the energy of the reactant, and this difference in energy between the reactant and the product is the delta G, or the change in free energy or change in enthalpy depending on what you are plotting on the y axis. So, this delta G of reaction is given by the difference in energy of reactant and product, but another important thing is how high is this maximum compared to what was the original energy of the reactant, and this difference is called the activation energy. And so, for the reactant to become a product, it has to go through this maximum. So, it has to gain energy which is equivalent to this difference in energy, and this difference in energy from this maximum to the energy of the reactant is called the activation energy or the activation barrier, and the reactant has to cross over the activation barrier to form the product. Now, in an uncatalytic process where there is no catalyst involved, this is the profile. If you add a catalyst, then the profile gets changed, and you may have a maximum which is much lower in energy than the maximum in the uncatalytic process. So, what has happened is the activation energy of the catalytic process has been reduced by the catalyst, and this is the key concept of the kinetics in the presence of a catalyst. The activation energy is decreased when the catalyst is present. You may note that there is no change in the free energy of the reaction, because that is given by the difference in the reactant and product energy, and this difference remains constant whether you use a catalyst or you do not use a catalyst. So, this maximum in the catalytic process is much lower than the maximum in the uncatalytic process, which means the activation barrier is reduced. Now, you can see several maximas here. So, you may have 1, 2, 3 activated complexes, and this the situation of the molecule at this energy, if you can find out what is the structure of the molecule at this stage, then that is called the activated complex, and the structure of the activated complex you can think about it, or the transition state. And in between two such small maximums, you see there is a valley, there is a minimum, and there is another minimum here, and these are called intermediates. So, in a catalytic process, you not only lower the activated the activation energy, but you may also end up with intermediate states, and the intermediates can be isolated. They may be stable for a short amount of time and can be isolated or seen spectroscopically. Their signatures can be seen spectroscopically. So, overall the reaction activation energy is altered, intermediates formed are different from those in non-catalytic reaction, and the reactions proceed under less demanding conditions. So, you can do reactions much more easily in the presence of a catalyst. We may, as already mentioned, the catalyst does not vary the change in free energy, and the equilibrium constant is related to the change in free energy, and since the free energy does not change whether you are doing a catalytic reaction or a non-catalytic reaction, hence the equilibrium constant is also does not change in the presence of catalyst. What the catalyst does is merely change the pace of the process or the rate of the reaction, and the 2 points which one has to remember in catalysis is the thermodynamics provides the driving force for a reaction, and the presence of catalyst changes the way how the driving force acts on that process. So, the driving force is the delta G, and the rate of the reaction using a lower activation energy is the change that catalysts provide to how the driving force will act on that process. Now, there are different types of catalysts and catalytic reactions. If based on its physical state, whether it is a gas, liquid or solid, you can have different types of catalysts. Then based on the nature of the substance, whether it is an organic compound, it is an inorganic compound, you have an inorganic catalyst, you have organic catalyst. All the enzymes in our body are organic. So, they act as organic catalysts, but there can be some inorganic metal atom containing enzymes also. There are enzymes where you may have some inorganic part also in enzymes. Now, depending how the catalyst works, whether it works in solution in with another ion or in a solvent where it is miscible, then you call it a homogeneous catalyst. Similarly, in the gas phase, if everything is a gas, the catalyst is a gas and the reactants are gases, that is also a homogeneous catalytic process. Whereas, a heterogeneous process involves more than one phase. So, you have a catalyst which may be a solid, and you may have reactants or products which are in solution or which are liquids. So, when you have 2 or more types of phases, then it is called a heterogeneous catalysis. So, you have homogeneous catalysis and heterogeneous catalysis. Then depending on the type of action of the catalyst, whether it is a acid base. So, acid catalyzed. So, you put some acid and it catalyzes a reaction, or you put a base, you can catalyze the reaction, or you have enzymes. So, that is enzyme catalysis. So, you have acid catalysis, base catalysis, enzyme catalysis. Then if you use light, which is going to be the major discussion in our next part of the lectures. So, you can call it photocatalysis, because you are using light, and this light can be in the ultraviolet region or in the visible region or in any other region, but mostly the reactions that we are interested in are in the visible or ultraviolet, because we want to use the solar radiation. And so, photocatalysis is a type of catalyst which depends on the presence of light during the catalytic process. Then you can do electrocatalysis, that means in the presence of a electric potential or when you pass a current, then you can do then you can alter the rates of reactions, and that is called electrocatalysis. So, these are different types of catalytic actions based on the type of whether it is an enzymatic reaction or it is a photocatalytic reaction or electrocatalytic reaction. You can have different types of names for this catalytic processes. Now, there are many applications of catalysis, as we discussed in the initial slides. Nearly 90% of the industrial processes which make chemicals involve catalysts, and so there are lots of applications of catalysis. Example, in all chemical industries we have some steps which involve catalysts, like in the petroleum sector, when you want to break down the petroleum which is obtained from the oil after drilling the oil, then you want to break down the petroleum that you got into different fractions of hydrocarbons. You may need catalysts, and these are called cracking catalysts, because they are cracking the hydrocarbons of some long chain hydrocarbons into smaller chain hydrocarbons and to separate them. So, in the petroleum industry, in the energy sector, in the fertilizer sector, pharmaceutical sector and fine chemicals, in all these industrial chemical industry plants, you will need catalysts in some process or the other. Then in environmental applications, where you want to reduce pollution, you can do several processes like pre-treatment using catalysts which reduce the amount of waste or change the composition of the emission, such that the emission is less toxic by using a catalyst in the process during the exhaust. If you can change a gas like carbon monoxide to a less toxic gas like carbon dioxide. So, that can be done using some catalyst. Similarly, you can, if you can change the carbon dioxide into some hydrocarbons that or some sugars, that would be even better for the environment. So, you can do pre-treatment, then you can also do post-treatment. Once the toxic thing has formed, then can you treat it to reduce and convert the emitted toxic substances. So, that is post-treatment. So, again continuing on pollution reduction, you can convert harmful gases to non-harmful gases. Like I said, from carbon monoxide you can make it to carbon dioxide, or carbon dioxide can be changed to hydrocarbons or sugars, and that is what is being done in converting harmful gases to non-harmful ones. Then liquids can be depolluted by changing the toxic liquid in a non-toxic liquid. Then you can change the odor of the liquid. For example, the liquid is not very toxic, but it has a bad odor. So, then you can use a catalyst to deodor the liquid. If the liquid has some color, you can remove that color, that is decolorization, using a catalyst. then this was how you handle liquid pollutants. Then solid pollutants in landfills and factory waste, you can use catalysts to reduce the toxicity of the solid waste. So, you have applications of catalysis in large amount in industries, chemical industries, and also in significant amount in environmental applications in remediation of pollution. For a good catalyst, what are the key requirements? One is activity. So, it should be able to enhance the rate of the reaction which you desire, and the second is selectivity. The catalyst should be able to actively promote one particular reaction which you desire. It can, if it promotes 2 or 3 reactions, then you will have 2 or 3 byproducts, but if you want only one product selectively, then the catalyst should be promoting only that particular process, not any other process. So, it has to be very selective, and this is sometimes more important than the activity, and sometimes it is more difficult to achieve. So, selectivity of a catalyst is highly desirable, and sometimes it is quite difficult to get a catalyst which is very good catalyst in terms of its activity, but may be not so good in terms of its selectivity. So, an example of a selective oxidation of nitric oxide to nitrogen dioxide is in the presence of sulfur dioxide. So, sulfur dioxide acts it can be a competing gas. So, if you want a catalyst to only oxidize nitric oxide to nitrogen dioxide, but not oxidize sulfur dioxide, then you need a very selective catalyst to act on nitric oxide. Then the catalyst itself should be stable, because you want to use the catalyst for several hundreds or thousands of cycles. So, the catalyst itself should be highly stable. It should resist deactivation, which is caused by impurities. Example, lead in petrol can poison. So, lead in several of our gasoline or petrol, as we call, we have these impurities, and these impurities can act as a poison or catalytic. It will cause a deterioration of the catalyst, or there can be thermal deterioration. There can be volatility and hydrolysis of active components which are part of the catalyst. Other thing is, especially if it is a solid catalyst, you can have what is called attrition, when due to mechanical movement or pressure shock, these solid catalyst can become a different morphology can be obtained due to the mechanical movement or pressure shock, and that will change. The change in the morphology or the surface will change the stability of the catalyst, and it may also change the activity of the catalyst, because catalysts are highly sensitive to their morphology, their surfaces, and since the active sites are present mostly in the surfaces and the edges and the defects on the surfaces. Hence, any change in the type of surface or morphology will significantly affect the ability of the catalyst to act as it would in its optimal morphology. So, a final thing, but a most important thing, a solid catalyst should have a very large surface area, because in a solid catalyst most of the reaction is at the surfaces as mentioned earlier, and the active sites are all on the surfaces. So, if the surface area is very high, you have a high proportion of active sites, and hence the catalyst can act much better. So, the activity will be very high when the surface area of the catalyst is very high, and typically you use very fine particles as catalysts. The reason is you want to have high surface area. In addition, you can enhance the surface area by making the solid into a porous structure. So, if you have a porous structure, the surface area again will be very high and you will have high activity of the catalyst. So, this was about generally about all about catalysts. Now, let us come to photochemical reactions, because you have to merge the photochemical properties and the catalytic properties to get a good photocatalyst. So, what are photochemical reactions? Typically, any reaction which is initiated by the absorption of light or photons, and then you can define what is called the quantum yield. In all photochemical processes, in all photocatalytic reactions, you may have to give a number which is the quantum yield. So, what is the quantum yield? So, the number of specific primary products, example a radical, a photon excited molecule or an ion. So, when light is absorbed or photons are absorbed by the photocatalyst, then you may generate a radical. So, a radical is highly reactive because it has an unpaired electron. You may have a photon excited molecule, a molecule having in the excited state, or an ion, a photo excited ion, and these primary products, these are called primary products, can be formed by absorption of each photon. So, how many such primary products are obtained by the absorption of one photon is called the primary quantum yield, given by the small f. Now, the number of reactant molecules that react as a result of the photon absorbed gives the overall quantum yield, which gives the capital F. So, you have two quantities. One is the number of primary products, or that is how many of radicals or how many photo excited molecules or how many photo excited ions are formed from the absorption of one photon is given by the primary quantum yield. However, the number of reactant molecules that react, here it is the number of excited molecules or radicals generated. Here it is number of reactant molecules that will react as a result of one photon, that is called overall quantum yield or capital F. So, this you can understand by looking at the following reactions. So, this is a reaction of hydrogen iodide in the presence of light to form hydrogen and iodine atoms. So, what has happened in this step is you have taken assume one photon of light with energy h nu. So, light you are using a frequency nu and small h is the Planck's constant. So, one photon when it falls on hydrogen iodide creates one H and one I, and so since there are two such particles, the primary quantum yield small f is 2. Then this hydrogen iodide, which is the reactant in the overall process, then this H again reacts with hydrogen iodide to give you H 2 plus I. So, overall in this process you use 2 H I's. Only one photon was used in this overall process, but 2 H I reacted. So, again the overall quantum yield capital F is 2, because 2 H I molecules reacted with the absorption of only one photon. So, I hope this is clear that you have a primary quantum yield is the number of radicals or photon excited molecules which are being created when one photon is absorbed. And if you look at how many reactant molecules reacted based on one photon, then that is called the overall quantum yield and is given by capital F. Now, you can have a very large capital F, it can be 10,000 or even more in certain kind of photochemical reactions, and these are chain reactions, and these are known, and several chain reactions are known, and many of them are actually photochemical reactions. That means, they are initiated by the absorption of a photon, and it can give rise to several reactions as a chain, and ultimately you can get several molecules of reactant react, and so if 10,000 molecules of some molecule A react to give products after absorbing only one photon, then your overall quantum yield will be several thousand, because you used only one photon and the reactants kept reacting and exciting one molecule or the other without absorption of any further photon. So, the overall quantum yield will be very high. Now, the quantum yield of a photochemical reaction depends on the wavelength of light. So, if you use a light of a particular wavelength, you may have some quantum yield. If you change the wavelength of light, then you will have some other quantum yield. So, that is another thing which you can study. For the same reaction, use light of different wavelengths, and for that then you have to use different kinds of light sources. So, if you are using a laser, then you have to use a laser of different wavelengths. Now, continuing on photochemical reactions, the wavelength selectivity of a photochemical reaction we just discussed, that a light of a particular wavelength may only excite a specific type of molecule, and hence the quantum yield of a photochemical reaction may vary with the wavelength of the light which you are using. This another important thing is, if you have isotopes. So, different isotope species, since they have different mass, hence different frequencies are required to match their vibrational rotational energies. The vibrational rotational energy depend on the mass of the constituent atoms, and so if you have isotopes, you may have the same molecule, say H2O, but if you have H2O and D2O, they are similar molecules, but their mass has changed, because you have replaced hydrogen with its isotope, which is deuterium. And so, this reaction shows that if you have iodine chloride, which is having iodine in with a mass of 36, and you also have iodine chloride where the iodine isotope 37 is present. So, you can have these kind of molecules which are specifically made with only iodine 36 atoms, and another molecule made by only iodine 37. So, this is isotopic iodine chloride. If you react them in the presence of light, then it may happen that only one of the chlorine is excited. So, in iodine chloride having the atomic number, the mass number of 36 is not getting excited, because this chlorine is not getting excited or not absorbing the photon. Only this chlorine, which is 37 chlorine. So, ICl will get excited by that photon, since 37 chlorine is getting excited, and so you can write with the star showing this is the photo excited molecule. And then this photo excited molecule can do further reaction. For example, in this case it is bromobenzene, and this 37 ICl excited molecule reacts with bromobenzene, and hence the chlorine which is substituted in the bromine position. So, from bromobenzene you can get chlorobenzene, and if you find out the mass of this chlorine group, which you can do by several techniques, then you will find that this chlorine has a mass of 37, and that allowed people to understand this mechanism, that since only chlorine 37 is present in chlorobenzene, then it should be possible only for the 37 iodine chloride to be photo excited, and hence this mechanism was arrived at. Now, similarly, there is another process where the molecule which is being excited is not actually the molecule which you want to react, but that excited molecule can then transfer its energy to the molecule of interest. This then is called photosensitization. So, the molecule A which you want to react, that is the reactant, may not be absorbing the light, and so it will not get photo excited. But the molecule B, which is in close proximity with A, can be excited by the light which you are shining on the material. So, if B can get excited by the light which you are using and goes to an excited state, then it can transfer its energy to A and then A gets activated. So, this is called photosensitization, and here B will be called the photosensitizer, because that is the molecule which is getting excited and sensitizing A. So, if you look at a reaction of mercury with hydrogen using 254 nanometer light. So, this kind of monochromatic, which means you are using light of only one wavelength. Normally, you can get in lasers where you can have a very monochromatic beam. Otherwise, you will have to use certain kind of filters, etcetera, where sometimes it is not so monochromatic. But if you have this 254 nanometer light and you do this reaction, then only mercury gets excited, the hydrogen does not get excited, but this excited mercury then reacts with hydrogen, and then you get the splitting of hydrogen molecule. So, mercury here is acting as the photosensitizer. This hydrogen once produced can then react with carbon monoxide to form sugars, and then those sugars like can be reduced with hydrogen gas to form formaldehyde. So, these are a reaction where you can understand what is a photosensitizer. So, typically what is the photocatalysis process is that you have a catalyst and it activates or it increases the rate of a reaction in the presence of photons, in the presence of light. So, that is photocatalysis. In any conventional redox reaction, the oxidizing agent should have more positive potential. So, in photocatalysis, how it is different from any any oxidation or reduction reaction is that simultaneously you are doing both oxidation and reduction, and the redox couple should be capable of promoting both the reactions, and then only it can act as a photocatalyst. So, there are several types of photocatalysts one can discuss, but as you will see that semiconductors with a reasonable band gap are some of the best photocatalysts that you can get, because in metals you have no band gap, the conduction band and the valence band are overlapping. In the insulators the band gap is very high. So, ideally in the semiconductors you have a reasonable band gap, and that is important for doing photocatalysis. So, what is photocatalysis? In a schematic view is you have in this is the process of photosynthesis, where photocatalysis is taking place. So, you have this green leaf which has this chlorophyll which absorbs this solar radiation, which acts as a acts like an antenna and then picks up the solar the photons from the solar energy, and in the presence of carbon dioxide and water it can gives rise to starch and oxygen. So, you can get a carbohydrate and oxygen in the presence of carbon dioxide and water and light, and this light harvesting is done by chlorophyll which is present in the plant in the leaves. This the other thing is what a lab made photocatalyst does. This is a natural process. A photocatalyst can take solar radiation, and if you have an organic compound, it can change the organic compound into carbon dioxide and water. So, in the presence of an organic compound, say a carbohydrate or a hydrocarbon, in the presence of water and oxygen, a photocatalyst can change it to carbon dioxide and water. So, this is little the opposite of what we are doing in photosynthesis, where we are making starch and oxygen using carbon dioxide and water. Here we are taking an organic compound and like a carbohydrate can be taken or a hydrocarbon. In the presence of water and oxygen, you are producing carbon dioxide and water. So, that is what the photocatalyst is doing. So, this is another comparison, that if you have photosynthesis and artificial photosynthesis, where a photocatalyst is being used. So, the comparison is in naturally what is photosynthesis is in the presence of solar radiation, the plants are using carbon dioxide and water to produce sugar and oxygen, and this much chemical energy is being used, because the energy, the delta G is not negative, the delta G is the difference of this and this energy, and that is positive. So, the energy of the final products is higher than the energy of the lower the reactants, and so you have to give this amount of chemical energy which the plant has and generates, and it uses it to make sugar. In the artificially in the lab, when we try to do the same thing, the same photosynthesis, that we call it as water splitting reaction, because the starting material here what we take is water, and the product instead of sugar what we get is hydrogen and oxygen. So, because in water splitting your reactant is only water, in the presence of the catalyst this water can be broken apart or splitted in the presence of solar radiation and the photocatalyst to hydrogen and oxygen. And again you have to give energy of the order of 237 kilojoule per mole. So, this is also a reaction which needs energy. So, you can see some similarity between photosynthesis and water splitting, and hence water splitting reaction is called artificial photosynthesis, and there is lot of research in this area to mimic the reactions in a green plant. So, this can be called a leaf mimic if you can find good photocatalysts which can break water into hydrogen and oxygen in the presence of sunlight at a decent rate of reaction. So, that is important. To make it efficient photocatalyst, you must have a reasonable rate of reaction. So, design of photocatalytic materials, how you design what will be a good photocatalyst. So, there are certain characteristics of these materials, and one is the band gap, and I said that you cannot use a material which has a very high band gap, because then you will need light of very high energy, but you want to use light which is easily available, and which is the light which is easily available is the solar radiation, and solar radiation has got distribution of frequencies, but most of the frequencies that you get are lying in the visible and the ultraviolet which you want to use. And so, the band gap of the material that you want to use, the semiconductor material, should be in that region of visible and ultraviolet. Then carrier transport, because you will have electrons and holes, and these have to be transported to two different electrodes to generate some current based on photocatalysis. Hence, carrier transport is important. The carrier transport and band gap both are affected by the crystallinity of the sample. So, how much crystalline is it, because an amorphous solid or a poorly crystalline solid will have a slightly different band gap, and hence that will affect the photocatalytic process. Then surface area we have already discussed. Very high surface area means very high number of active sites, and so the reaction rate will be very high and it will be a good catalyst. Then the stability of the catalyst is important, because you want to use and reuse this catalyst several times. So, these are some of the controlling factors which you think about when you are trying to design photocatalytic materials. So, why semiconductor? Because as I said, in metals there is no band gap, you can only do reduction or oxidation. In insulators you have very high band gap, high energy requirement, and this you will not be able to do with the visible radiation or near UV radiation. Now, typically you can see that a semiconductor has this band gap, the conduction band and valence band, and this is the energy difference of what you do need for water splitting. And if you have a very high band gap, which is in insulators, or no band gap like in metals, then that does not help this water splitting reaction, but a reasonable band gap like present in several semiconductors can help this splitting of water due to similar type of band gaps. So, again why semiconductors are chosen as photocatalysts? Because for conventional redox reactions, one is interested in either reduction or oxidation, and whereas in a photocatalyst you have to do both reduction and oxidation. Now, if you consider the oxidation of iron to iron 3 plus Fe2 to Fe3, then you can use an oxidizing agent to carry out this oxidation. That is given by the which will be a good oxidizing agent, that you have to see the relative potentials, of the oxidizing agent with respect to the redox potential of this Fe2 plus Fe3 plus couple. The oxidizing agent should be chosen such that it should have a more positive potential with respect to Fe3 plus Fe2 plus. That means, the valence band should be lower than the valence band of the Fe2 plus Fe3 plus couple. So, the energy required. So, you will be able to transfer a hole into the iron 2 plus to convert to iron 3 plus, if the energy of this the valence band of the semiconductor is lower than the energy of this Fe2 plus Fe3 plus couple. Whereas, if you want to do a reduction, then of course, you will have to choose a different kind of photocatalyst, and where you will be dealing with the conduction band and you want to transfer electrons to carry out the reduction. Here we are talking of oxidation, and hence we are talking about holes which are important, which will carry out the oxidation. And if you are dealing with a reduction reaction, then you will discuss the electrons which are normally present in the conduction band and which can be transferred to the couple. So, depending on whether you are doing oxidation or reduction, you have to know which system to choose from the potentials which are all tabulated in several books. Now, if this is a catalyst particle, several processes occur when light falls on this catalyst, which is a semiconductor. So, in the bulk, certain processes will occur when light impinges on this catalyst particle. So, in the bulk you have this band diagram for the material, for the catalytic material, and when light strikes, actually you will be generating holes in the valence band and electrons in the conduction band. Now, the electron and hole together is called an exciton, and this pair of charges is very important, that they should not recombine. So, if they recombine, then they will give out a photon. So, recombination between these two levels will not allow you to carry out any catalytic reaction. So, it is important for light to produce these holes and electrons, but then it is also important that these two do not recombine fast and the time of recombination is long. So, if that is true, then the electron which is here in the conduction band can go in one direction, and if the hole can be taken to another direction, then you can do two things. You can reduce using the electron and surface recombination, you can reduce something, and on this side using the hole on this part of the surface, you can oxidize D to D plus. So, both these things can happen. So, you can take electron can go to the surface. So, actually this is the process, the electron is going to the surface. If it recombines, then it is lost, the electron will be lost if it recombines with the say a positive surface defect. But if the electron goes to the surface without meeting a plus charge, then the electron can reduce A to A minus. So, this is the electron that is important and is fruitful as in the catalytic process, and this is the hole which is fruitful. So, you do not want process like this, these are volume recombination, that means the electron met a hole in within the solid particle. So, it is a volume recombination. Here the electron met the hole on the surface, and so it is called surface recombination. Either of the recombinations are not good for photocatalysis. For photocatalysis, you want both the electrons and the holes to migrate to long distances to different parts of the particle and do catalytic reactions on the surface, and two processes can occur, both oxidation as well as reduction. And this is again shown here, that if you have a photon, electron hole pair is generated and the electron goes to the surface and will reduce water to hydrogen, and the hole goes to another part and will oxidize water to oxygen. So, this is a water splitting reaction, where water using the electron and hole can change to hydrogen and oxygen. So, this process basically is explaining the photocatalytic water splitting. So, in a water splitting reaction, both redox reactions occur simultaneously. You have reduction of protons to give hydrogen, as well as hydroxyl ions will react with holes and to give you oxygen. So, hydrogen and oxygen both will be produced, and a good photocatalyst is for water splitting is one which can promote both these reactions simultaneously. Now, it is known that the water couple that is given in this diagram, this couple that H plus H2 and water oxygen, this energy gap is around 1.23 volts. So, you have to give energy of 1.23 volts or potential of nearly 1.23 volts by any reaction which you are doing using the photocatalyst. Now, the top of the valence band and bottom of the conduction band are separated by this, that is what it means. And in addition to the condition that the potential corresponding to the bottom of the conduction band has to be more negative, and so not only you must have this difference 1.23 volts is the gap, at least should be there between the conduction band and the valence band of the semiconductor, but it is also necessary that the potential corresponding to the bottom of the conduction band has to be more negative, while the potential of the top of the valence band has to be more positive compared to the oxidation potential of this reaction. So, these are some key factors to choose semiconductors which can act as photocatalysts for water splitting reactions. So, the criteria for the selection of the semiconductor materials, essentially we discussed what kind of band gap should be there, where should be the top of the valence band, and where is the bottom of the valence conduction band. So, top of the valence band, bottom of the conduction band and the band gap, these three factors are very important in deciding which semiconductor you will use to achieve photocatalysis for a particular given system. Typically, ionic solids, in ionic solids the ionicity of the metal oxygen bond increases, the top of the valence band becomes less and less positive, and this is due to the bonding between the orbitals and the of the metal and the oxide ions, and the bottom of the conduction band will be stabilized to higher binding energy due to the positive charge of the metal ions, which is not favorable for the hydrogen reduction reaction. So, because you want the bottom of the conduction band, you want it to become lower, the bottom of the conduction band should become higher and the top part of the valence band should become lower for the reaction to occur. So, more ionic the MO bond of the semiconductor, the less suitable the material is for the photocatalytic splitting of water. And so, if you take something like titanium dioxide and cadmium sulphide, titanium dioxide is more ionic and cadmium sulphide is less ionic. So, cadmium sulphide is a better material for photocatalytic splitting. Of course, it may have other problems, etc. Now, the bond polarity or the ionic bond can be given by this expression of percentage ionic character, and it is given as a exponential of the difference, the square of the difference of the electronegativities of the binary system. Say suppose it is a metal oxide, metal and oxygen. So, based on that, you can see there are a lot of materials which are semiconductors and their metal oxygen percentage ionic character is listed here, and you see the red ones, strontium titanate or barium titanate or potassium tantalate, very high ionic character and may not be suitable for the photocatalytic water splitting in terms of the band gap, which is greater than the water decomposition, right. The percentage ionic character you want is to be low, and you see many of these telluride, arsenide, selenide semiconductors have very low percentage ionic character. So, that way they are much better, but they may have other defects for the photocatalytic reaction. So, one has to make a judicious choice of various properties to choose a final photocatalyst. Now, one can also use a co-catalyst along with the photocatalyst. So, people many times use metals like copper, nickel, platinum, rhodium, etc. people have used for trapping electrons along with the catalyst. These metals help to trap electrons, and then so the hole is separated from the electron, the hole is in the semiconductor, and these co-catalysts can trap the electrons. Or if you use a metal oxide as a co-catalyst like nickel oxide, ruthenium oxide, they can trap the holes, and eventually what you do, you increase the lifetime of the excitons and recombination is effectively reduced. So, the energy bands of the photocatalyst are modified by the co-catalyst, and hence this electron trapping or hole trapping will increase on depending on whether you are using a metal or a metal oxide. Overall, the result is you help slow down the recombination of the electron hole pair. So, with that we come to the end of our lecture today, and this is the first lecture on photocatalysis, and we will continue 2 more lectures on photocatalysis. Thank you.